So, welcome everybody to this talk. So I'm going to give you a brief weather report and overview of the 2 years old now incubator project Unikraft. My name is Kuenzer. I'm the lead maintainer of that project. We're currently a team of 4 maintainers that are taking care of that. And yeah, let's start. Can I briefly ask you guys, who of you ever heard of unikernels and who didn't? So raise your hands if you know what a unikernel is. So it's roughly the half. Okay. So then I will start with a really short introduction so that we are all on the same page. But this will be really quick. So a unikernel, as we understand, is a specialized system. So let's take this picture. On the left side, you have a traditional VM where, let's say, standard cloud deployment, you have roughly 1 application running per VM because of isolation reasons, a general purpose kernel underneath. And what we want to do with the unikernel is taking the same isolation boundary, but we start optimizing the kernel layers underneath. So the idea is, since you anyway run 1 application in the isolation boundary, you could modify the kernel layers to make it more beneficial for your application. So one important thing is that unikernels are purpose-built OS layers. So you have a thin kernel layer, has only the stuff that the application needs, and on the other side, only the stuff what your hypervisor environment or bare metal environment needs. So you have only, for instance, on Zen, you have only the Zen drivers within that OS layer. As simplification, because we know it's just 1 application, you can build a monolithic binary. You can give up address isolation between kernel and application, so you get a single flat address space. And if you do, as we do with Unicraft, making use of specialization of these kernel layers, you get quite a lot of performance and efficiency benefits. You have a reduced attack vector because you're basically throwing out all components that a standard kernel or standard system deployment actually doesn't have and you don't need. And the memory footprint is quite small. So we started with the Unikraft project because the unikernel project that were out there were still hard to use or were kind of limited to specific use cases. So we wanted to have something that supports actually a really wide range of use cases and is feasible for almost all unikernel projects that you have. Another motivation for us was that we wanted to simplify the building process and optimizing process. We wanted to simplify porting of existing applications. Wanted to create a common and shared code base so that other unikernel projects, can make use of it and can contribute back to individual pieces. So that is kind of, the whole open source thing beneficial for all projects in the end, right? In terms, let's say, one is developing a specific driver so that also other unikernel projects can just use it. And of course, we want to have a really wide range of different hypervisor and CPU architecture support. And this is where we came up then with Unikraft, where we go with the concept that everything is a library. This goes as far as that you even say that each operating system component, like a scheduler or a memory allocator, is a library and replaceable. And we have 2 components, which is a library pool and a build tool. So as a short recap, we distinguish roughly between main libraries, which are independent actually of a particular platform implementation or architecture implementation. Then we have platform libraries, which implement specific calls to the particular hypervisor environment. So for instance, the Zen one has Zen hypercalls, Zen drivers. The KVM one speaks Vert.io and KVM specifics and so forth. And then we have some architecture libraries which are needed for implementing some CPU-specific requirements. And the idea is you come with your application or you develop it, pick the libraries out of the pool that you need for your OS features, which is file system support, for instance, or scheduler, or even you say it's single-threaded, you don't need scheduler, so you keep it out. And then build system is then building you multiple images depending on your selection, each of them is then optimized for your selected target execution environment. And our build tool that we have is actually makefile based. We stole kconfig from Linux. Also, the whole flow is really close to what you do with the Linux kernel. So you have make menu config, you do the selection of options over there, you have a .config. And right, you save your config and type make, and the whole thing is start to build you the images. So this has a really short recap. Now let's talk about the community status and what we achieved so far. So we originally started as an NEC internal project early 2017. Then we started with the build system. We took pieces from Minimas and at that time Solo 5, which was like the KVM equivalent of Minimas. And after discussing with the Zen board and getting all these procedures set up, we were finally able to do the public launch in December 2017. We started with the release number 0.2, so 0.1 was kind of an internal release number. So we are now in Zen incubator project, and at that time we had support for Zen on ARM32 boards, or ARM v7 actually. KVM, Zen, and Linux support for x86. We came with the ported binary body allocator from Minimas and had a really rough implementation of a cooperative scheduler. In February 2019, we had the next release, so almost a bit longer than a year, like 1 year and 2 months or something, where also ARM was contributing with ARM64 support for KVM initially. We introduced networking. We have initial VFS, which we ported from OSV actually. So it's kind of really a full-blown VFS support that you can select now as a library. We have an in-RAM file system, and because many applications need libcs, right, we started with newlib as the first library for having a libc. And then in the upcoming release, which we kind of expect as the schedule looks right now, it's probably in the September timeframe, we'll come with more language support. We have finally full C++ support, including exception handling and all the standard libraries that the C++ application need. Python we have, and also some other languages. Then block and console device driver support. We have, until then, also 9PFS file system support for Zen and KVM, so that you can share a host file system with your guest. And then a lot of libraries that basically were also needed by these different languages. For instance, libunwind or pthread embedded, and these things that you need for your applications. To give you a short overview how the, let's say, how the contribution was going over the time, you see on the left side that the left bar is the year 2017. This is actually the year where we launched the project in December, so no surprise, it's just NEC that contributed. This was like a big flush of the internal code, so we had 3 contributors there, and the project launched. But already in the first year, we did some fundamental noise, I would say. So we got roughly 20 contributors over that year, mostly from a university in Bucharest where we have collaborations with, and we started student projects there, and the students were really motivated to contribute to this project. Also, ARM joined us, and we have also some other individual contributors that did some individual pieces here and there in the system. And then you see 2019, and then as you may know, we're in the middle of 2019, so this is like a half year number. We have already much more changed or contributed lines of code 2019 already. This is also due to the fact that these lots of student projects that we started 2018 are now finally submitting their projects upstream. So expect also much more to come. And in this bar, there is also still, we have currently a huge stack of patches which are under review, which are not taking into this number yet. So there's, for instance, also a huge block of ARM contributions that we're currently reviewing, and it's not part of this number. But I think it looks quite good already, what we have achieved here. So the tools that we use, we have, let's say, a basic documentation online on a domain called unicraft.org. We generate that with Sphinx, as the Linux kernel folks also doing. Those documentation tree is based in the repo in the doc folder. And it has for now basically tutorials or more description how to do things, how to port the library and so forth. Longer term, we would like to have also, automated generation of description of API and argument calls and so forth. For patch reviews, I think last year we decided to go for patchwork to get that a bit more organized than just the mailing list. So we have our instance running on patchwork.unicraft.org. And we use it for coordinating all the reviews of the patch series. And it's like for the community a way to get a bit more details about what is going on with their patches and if someone is currently looking at it and who it is actually. And also at the same time has some nice command line tools that we can use too for getting the patches from the mailing list and testing them. And then we noticed we really should have an automated testing framework soon. The earlier the better, because we have so many libraries, different configurations and variations that you can do with Unicraft, and they should be tested. So what we have today still, and this is kind of more bit taken as an example from our mentoring project, the Zen project, and we have these two branches, master and staging. On staging, we have the latest accepted patches. So currently, if you do development, you should always take the staging branches. And on master, we do a manual follow-up on the staging branches with let's say, manual testing. The release tags are also on the master branch. What we want to do is kind of more, so we start looking into Jenkins actually to have the common combinations and configurations and putting in libraries in and out. We wanted to do that automated and do also execution tasks on the different hypervisor environments that we support and also the different architectures. And of course the goal is to integrate that into the reviewing process so that we also know that the patches that we're accepting also not breaking anything existing. So on the really interesting part here is this presentation where I want to give you an overview of projects that at least from the NEC side we are kind of coordinating or involved in. So also to give you an idea in which direction we're going currently. Also I need to add here that so far we had focus in that project for functional completeness first, in order to learn also early which requirements we need on the decomposed OS libraries, and also we wanted to achieve quite early noise in order to grow the community. And this looks like now lots of projects we are working on, but we still have in mind that at some point we need to go in the phase for optimizing and actually tuning the interfaces we do underneath. So one really interesting project, and I think this is kind of one of the items which will simplify the adoption of Unicraft quite a lot, is binary compatibility. So the idea is, or actually the problem that we still see, even if we have simplified the porting, but even if you do things like cross-compilation or you need to write makefiles and these things, this is still a developer thing to do. So it's still hard for some non-developers to build a unikernel if no one else did the port of the desired application yet. So what we want to do is providing an ELF, Linux ELF compatibility layer that you can select as a library, for instance, and that enables then that you can run the same executable, the same binary without touching it actually within Unikraft, which requires, of course, an ELF loader and a system call emulation. And for sure, we're also able to do there then some tweaks and tricks and tuning to optimize and specialize that unikernel further. But at least from the user perspective, they can run an unmodified binary, and it's probably making the burden much lower. Then we're working quite a lot of language runtimes. So we want to support as many higher level languages as possible, especially when we look at serverless use cases or IoT, where you have applications written, let's say in JavaScript anyways already, and the porting over there just means to have that runtime environment as a unikernel. And we're working, as you saw already in the announcement the slide before, on C++. Rust is one target we're currently looking at. Go is another one. Ruby, JavaScript, and of course Python. And I want to show you here one interesting early numbers that we got. How big such a unikernels actually look with the particular language environment. For instance, for Python 2 programs, we have two implementations. One is based on MicroPython, which is an embedded project for running originally Python programs on microcontrollers. There we get a Python environment with Unikraft running for Zen, and this is an uncompressed image with 828 kilobytes. If we use the standard Python 2 environment, this is roughly 3.9 megabytes. And the Go runtime, where the only thing that's missing is like your Go binaries that you link with it, it's roughly 552 kilobytes. So this is like the I find quite impressive low base for supporting other languages. Another area we're looking at is NFV, so virtualized network functions. The idea is here to package the network functions directly as a virtual machine with Unikraft. That is removing the maintenance effort for, let's say today virtualized NF functions where you have a standard OS underneath. You get rid of it. You don't have all these tools and whatever around that you also need to maintain and need to care about. So reduced attack vector too. The OS overhead gets more minimal so that you achieve better performance. The OS noise is minimal because you don't need to deal with preemption if you don't need for your the preemptive schedulers if you don't need that in your VNF and so forth. And you can achieve really high networking performance throughput. And we have this is kind of too fast. Anyway, we have two projects there. One is Click that we recently upstreamed. This is our, let's say, old, more or less research flagship, ClickOS. We ported that on Unikraft, which essentially becomes a programmable virtualized network functions where you can build a NAT or a firewall or a load balancer or rate limiter with a Click language. And the other project we're working on is Intel DVDK. So what we want to do, so Intel DVDK is actually a data plane, it's called Data Plane Development Kit. So this is quite famous in the meantime development kit for building network functions for x86 mainly. And what we want to achieve here is, because they do, they build the application for user space, do full kernel bypass, And we think with Unikraft you can get rid of the whole kernel completely and run that application directly as kernel and benefit from there. Another projects that we are doing is lots of application porting, also for us to understand what is needed from the OS layers, which libraries is a common set that we need. And we look here at typical cloud deployments. There we were working on web servers like, or I'm currently working on like Nginx or Light HTTPD. So we had one student that actually got Nginx running and achieves much higher requests per second as on a standard Linux deployment. Then databases, we looked at Memcached, Redis, SQLite. And we also, this looks a bit more far-fetched, but we also looked into machine learning frameworks like PyTorch. And we do all of that in order to understand or lower the burden further so that they get as minimal as possible effort for someone for porting a new application. So that the only thing that's left is like integrating it, the other build system to Unikraft and make it build somehow. Also here I can give you a number of an SQLite unikernel with Unikraft where we have like 844 kilobytes. And that's your whole SQLite thing. Of course, this one doesn't have file system support except just in RAM file system. But it also it gives already a nice baseline, right? How small this stuff can be. Another area we are looking at is DOM0 disaggregation. We had actually yesterday a design session about that topic. So what we're doing here is actually this typical thing, for instance, taking out the Zen store and run that as a stub domain with the unikernel directly on Zen and take it out from DOM0. The typical chemo deployment for HVM virtualization. We're also looking into getting that moved as a stub domain and taking out of DOM0. And last but not least is actually security hardening. This becomes now a bigger, interesting topic to work on. So actually we can say already we have a small attack vector because we specialize everything, but it's not enough, right? So you probably heard of this publication that the NCC group was doing and was telling about that the security is terrible within unikernels. But this was mainly due to the fact that all the existing unikernel environments didn't implement, basic attack prevention features like ASLR, stack canaries, page protection bits, and so forth. So what this is about is actually implementing that stuff to make have some prevention for attacks, because you still, even if it's a unikernel, you still don't want to get taken over by a third party. And another interesting point here is that we see that probably there's a potential, and it's maybe also a bit more a research question, if we can provide even enhanced protection features or prevention features by using our privilege mode, because we run everything in kernel mode, so we have direct access to page table manipulation and so forth. Means we could use that for our heap management for mapping pages on malloc and freeing them again, unmapping them when we free, so that this memory region gets inaccessible. Right. We have more talks actually about Unikraft today, mainly. So today is Unikraft Day at the Zen Summit. There is later a talk or actually two talks by the ARM folks about their work with Unikraft. So if you're interested, I really recommend to attend those talks. This is about porting it to Solo 5, which is now in the meantime a really minimalistic VMM that you can use for unikernels. Another talk is about all the work that ARM did for porting Unikraft to ARM64. And then there's another related talk from Marek regarding Mirage as a PVH, and one part of it is looking into if they could use Unikraft for their port. And then also we have another design session. Actually, one design session, the first one was yesterday happening already, but the other one happens today. This is for everyone that is interested in how this whole build system thing works and how can you do an own application port. So I'm going to use that design session to give a brief tutorial on how these makefiles look like and how Unikraft is actually building things. Okay, questions?
I'll hand the micro. So for the design sessions, obviously the schedule isn't locked yet, so that may still change.
Oh.
Yeah.
Okay.
So,
I was saying,
and you can still vote for, like basically go through the system and tell which sessions you want to attend, and that will ultimately affect the schedule.
But the other one is already.
The other one has happened, right? Yes. So obviously.
It did not reawake, right, like a zombie.
All right. So questions. Oh, I'm going to have to run all the way back.
Okay, so for context, the unikernel security paper that you just cited, I wrote that. I'm wondering if, like, depending on when you read that research relative to when you were developing this, why did you end up using newlib? Because I actually gave newlib quite a thrashing in that paper for basically not having any sort of modern memory protections. So
the reason why we took newlib, and actually I need to add, newlib is just one libc for us that we want to support. So we're also looking into muscle. And the reason why we took newlib first was it has more a focus on embedded environments. And what usually these software projects are doing, they give you a clear implementation API for your OS primitives. So it's much easier to port newlib than something like muscle. But actually muscle is something we have in Works too. The thing is that porting it to other than standard Linux is a bit harder because you need to provide the system call layer.
Okay, fair enough.
Yeah.
Other questions? Raise your hands.
Hi, Samuel. How to handle the port the application with dynamic library, the linking?
So that depends. Let's say, okay, with this binary compatibility layer, you would be able to load shared libraries as you do in Linux. If you have now an application and you put it, as a statically linked thing, you also will port the libraries that the application depends on statically linked to Unicraft.
Any more?
You mentioned Python support. Is that both Python 2 and Python 3?
So yeah, we're working on both.
Okay.
It's just that we are earlier done with Python 2 than with Python 3, but we are looking also in Python 3. I thought it's Python 2 as far as, but correct me if I'm wrong.
I think MicroPython's all Python 3.
Okay.
Okay. Last call.
Some exercise this morning, huh?
Did you look at the build center for like rump kernel where they have the cross compile thing?
Not yet, but we are going to do that. Especially after the
discussion yesterday, right? Okay.
Yesterday.
Okay.
We'll definitely look at it. So the only way you can port applications libraries for now is, in fact, by writing a Unicraft specific makefile and kind of, re-mimic the build procedure of your application. But another target is looking into enabling cross-compilation, which is kind of an instrumentation of the original build system to make that fit to Unicraft. And on the extreme spectrum is the binary compatibility where you don't need to rebuild actually, right?
Right, thanks.
Yeah.
Okay, then last call, final last call. All right, thank you very much.
Thanks.